pointer is yellow.
Okay. Good morning, everyone. Let me first thank Francesco and Samuel for giving this opportunity to me to present this work. This work is a joint work between, of course, myself, Javier Segurado, Andrea Pantaghini, and Javier Yorca. I'm going to talk about strain gradient crystal plasticity and discrete dislocation dynamics. And the Spain part of this collaboration took care of the discrete dislocation dynamics simulation. So the motivation for this work was just try to compare the results of strain gradient crystal plasticity with those of discrete dislocation dynamic simulations. We wanted to use the latter as pseudo-experimental results to identify the length scales involved in strain gradient plasticity. Actually, it turned out quite a difficult task because we found out some effect, which is the main title of this presentation. So this huge latent hardening size effect. So I think that one of the novelty of this work is this focus on the multi-slip behavior at the small scales. Sorry, I didn't mention that the size effect we want to model is relevant in the range between size of a few tens of nanometers to a few tens of microns. So in order to do this comparison, we took a very simple example. We consider a long strip sheared between two bodies in which these locations cannot penetrate. And sorry, there is some cut here, but in strain gradient plasticity, two relevant measures, actually in any crystal plasticity, relevant measures are the plastic distortion. This is just to introduce my notation, it's trivial stuff. You construct the plastic distortion by sum over all the slip systems of this product. M is the slip direction, N is the normal to the slip system. In this very simple case, this plane strain case, you just see edge dislocations, and so different slip systems are just different direction on this plane. And of course, the plastic strain is just the symmetric part of the plastic distortion. And with the gradient plasticity, usually we can qualitatively model two size effects. One is strengthening, so you decrease the size of the sample and you recognize a higher yield stress, which is this one. And the other different size effect consists of just a change in the strain hardening slope. So you go down in size and you see a variation in the slope of the strain hardening curve. And so the main effect is due to the pile-up of dislocation on the grain boundaries on the strip boundary, when you apply this shear, where the plastic strain has to go to zero because there the dislocations just stop. And in the main equation governing this discrete dislocation dynamics is this one, in which you compute the velocity of each dislocation in its slip system, and the resolved shear stress is due to the singularities of all the other dislocations within the sample, plus this sigma hat is due to the boundary conditions and to some image tractions you apply on the boundary of your finite element simulation to compensate the fact that these stress due to the singularities of other dislocations are in unbounded medium. So it's just a superposition. And this small b is the Burger's vector, and this is the drag coefficient. Of course, we didn't know which kind of size effects we could find by solving this problem with this dislocation dynamics. This is the reason why here there are question marks. So in order to make things easier, we just consider couples of slip systems symmetrically oriented with respect to the applied shear in such a way that at least in the strain gradient crystal plasticity model, the problem becomes just unidimensional. And about discrete dislocation dynamics simulation, you have a lot of parameters you got to choose to run the analysis, and like the Burger's vector length, the drag coefficient, and so on. We chose most of them like in other papers. Besides these 3 they are a little bit different, the obstacle strength, obstacle density, and source density. And these parameters are usually kind of difficult to be related to the parameters involved in the crystal plasticity model. And in the BD simulations, we took this strip, which is not infinitely long, it's just the length is a little bit more than it is 1/3 of, the length is more than 3 times the height of the strip, and we couldn't take it much longer because the analysis was very expensive. Anyway, this is enough to get rid of the boundary effect on the edge, on the vertical edge of this strip. We applied the total engineering shear strain of 2%, and you see the analysis must be very fast because of the physical meaning of the drag coefficient and so on, so the time is very small, and each analysis consists of 200,000 increments. They are extremely expensive, and we changed the total time of the simulation a little bit, but within this range we didn't find much rate sensitivity. So some results. Sorry, there is on the horizontal line you see the applied strain, which is actually the applied, I call it applied strain, is quite inappropriate, it's just the applied displacement divided by the strip H, and here you see the coefficient shear stress. These results are for just one couple of systems, okay, and they are actually the black curve is for system oriented like the shear direction. So in this curve you can measure kind of the self-hardening of the slip system, and the other 3 curves are related to couples inclined by pi/8, and they are related to 3 different samples. The 8 changes from 1.5 micron to 6 micron, and as you can see, there is each curve comes from the average over 3 realizations, and you can see a little bit of strain hardening variation, but no strengthening at all. So the yield stress is always the same. And now, when you add a second couple of systems, the second couple of systems is inclined at pi/5, and you see this huge latent hardening effect. So we give the sample one more possibility to glide, to develop plastic deformation, but in spite of this, the stress strain, the response is almost always stiffer. This is because as soon as a dipole of dislocation enucleates on these more inclined couple of systems, these new dislocations provide such an obstacle to the glide on the less inclined system that the response is like this. And this is just for one strip. I didn't want to superpose too many curves here, but then I'll show you more results. So as I said, there is quite a negligible rate sensitivity in this problem, and dislocation spacing at the end of analysis is about 0.1 micron. So now I switch to the strain gradient crystal plasticity model. It is based on the use of nice dislocation density tensor to describe the effect of geometrically necessary dislocations. So basically, nice tensor is constructed based on the incompatibility of the plastic distortion. And I won't give many details on this because most of you know all of this, I think, but let me just say that you can just a formula which is going to be used later, that nice dislocation density tensor can be also written in terms of this third order tensor. Sorry for the index notation, but it was probably most direct to see. So you see the projection of the slip gradient onto this third order tensor, which account for the crystallographic direction. T is the direction on the slip plane normal to the slip direction. And also nice dislocation density tensor can be written in terms of pure densities of dislocations, of edge and screw dislocations, defined just by projecting the gradient of the slip onto the slip direction, or for edge dislocation onto the transverse direction. And so how do we use the nice tensor within the theory? We just define a free energy composed by the linear elastic part plus a defect energy, which is a function of nice tensor. And this ingredient in higher order or conjugate gradient plasticity is expected to provide just strain hardening variation accompanied with diminishing size if at least the defect energy is quadratic in nice tensor, otherwise we have different effect. Sorry, here there is some cut. I just wrote that this is true in single slip, but if there is multi-slip, some other effects may be seen. And also we had some higher order dissipative terms, so I chose as higher order variables the rates of these pure dislocation densities, and I added to them also the projection onto the slip plane normal of the gradient of the slip rate, just to have one more variable. And this is quite phenomenological. The attempt is to model the dissipation, so the motion of dislocations. And usually this provides a strengthening. So we already saw that in dislocation dynamics we didn't see any strengthening. But first of all, we were planning to implement a quite complicated hardening in the crystal plasticity model, so we didn't exactly know whether these terms could deliver a different size effect. Second of all, it turned out that they are useful for the computation. For the finite element computation, these terms help in reaching convergence. And so the theory is constructed by the model is obtained, the equation governing the problem are obtained by constructed internal virtual work. You have the energetic part and the dissipative part. So red is the non-standard energetic term. There is a defect stress work conjugate to nice tensor. And in the dissipative part there are these omega stresses work conjugate to the three rates of dislocation densities, and this rho n, which is not dislocation density, is just an extension of the notation. Here in this form of the internal virtual work, just to try to be clearer, I put some constitutive choices, which are of course unnecessary to obtain the balance equations, but it's just a choice to try to be clearer. And so we have the Cauchy stress, the defect stress. This S stress is work conjugate to the slips, and then higher order dissipative stresses. And so the external virtual work is standard because we just use higher order homogeneous boundary conditions. So either the slip is 0 when dislocation pile up, or the higher order traction is 0 when dislocation can just exceed the boundary. In our benchmark, of course, our higher order boundary condition just says that the slip has to be 0 on the boundary where dislocations pile up, and this delivers this size effect. So standard arguments, integration by part, whatever, provide this higher order balance equation, which is an extended Schmidt law. The usual Schmidt law is without this last term, so it says that the resolved shear stress, the Schmidt shear stress, must be equal to this S stress. In this case, we have this extra term, and this micro stress accounts for all the contribution, energetic and dissipative higher order stress in this equation. And of course, we don't use in this benchmark these natural boundary conditions. As I said, we just say that each slip component has to be 0 on the boundary. So, constitutive choice for the defect energy, I chose this power law. I tried different, okay, first of all, when you define four-dimensional consistency, when you define the defect energy, you got to introduce this length scale, at least one. You can do more, but we just used one, and so this red L, I'm going to call it energetic length scale, and so changing this exponent n, if you take it 1, it's quadratic, and which is going to be the case in this in the results I'm going to show, because it's the best fit is the only one which just shows strain hardening variation, no strengthening. If you take it n equal to 0, it's the one homogeneous case, but that provides strengthening. And I think the choice of the defect energy, of course, it's one of the main important thing to be addressed in the near future. I think there are other possibilities. The logarithmic defect energy proposed by Samuel Forrest, and there are also more complicated defect energy, like the non-convex defect energy proposed by the group of Mark Geers, used in order to describe the dislocation patterning. But anyway, I think this is a very important issue to be addressed because it changes a lot of things. About the dissipative behavior, it's just viscoplasticity. So it's an extension of standard viscoplasticity, and instead of the usual slip rate, you have an effective slip rate, and there is this P norm, and you can introduce 3 different length scales. After some test, finally here we'll use the Euclidean norm, and we'll use all for all the dissipative length scales, we'll use the same number, which should be about 0 to avoid strengthening, but we'll take it as small as possible, trying to, we cannot take it really 0, because otherwise it's really hard to have convergence in the finite element simulation of this problem with gradient plasticity. And the little novelty of this modeling is that for the slip resistance, we have extended the classical Pierce-Azaro-Niederman latent hardening. First of all, straightforward extension, you just put the effective plastic slip rate instead of the usual one, so this involves the length scales. But then, in order to try to model somehow what we observed with dislocation dynamics, we had to put also this extra term in which this scalar dot alpha, let me just say, because it's quite complicated, let me just say that it accounts for the increment in nice dislocation densities on different systems with respect to the one you are writing the higher order balance equation on. And these coplanarity moduli in our simple case are just Kronecker delta. I give you more detail if you like, but this is okay. H lambda is the classical self-hardening rule of one of the most used, and that's it. So it's quite complicated. And okay, I may skip this this slide is just about particularizations of this model to other models present in the literature, but I'm going to skip this one. And I just wish to write, in this case, so far the equations were for a general case. Now this is a particularization for this symmetric simple shear, and I wish to write down the higher order balance equation, so the extended Schmidt law in terms of kinematics, just to highlight the two sources of coupling we have in these equations. One is kind of standard, is due to the defect energy written in terms of nice tensor. The other one is this complicated slip resistance in which there is latent hardening and so on, and the gradient extension of the latent hardening. So, the finite element model, I've implemented a user element in Abacus. So, since the problem is unidimensional, it's just these are just linear elements. The convergence. So my aim, since many friends of me, they implement strain gradient plasticity, and they usually their elements are general purpose elements. For instance, for plane case, and in order to have convergence, they usually use explicit integration scheme. I wanted an implicit integration scheme, and I was hoping that for just a Uni-X case I could reach convergence. Actually I could, but it was very hard. Just for half strip I had to put 72,000 elements, decreasing size from the middle to the boundary. The ratio between the smallest and the largest element is kind of 1/10,000, so it's quite crazy, because you cannot, all the nonlinearity goes to the global iteration scheme. So in order to relax to allow convergence, you got to just to increase the mesh. You cannot put many other ingredients in the algorithm if you have no access to the global iteration scheme. And this is not the case, because I had the bad idea to use Abacus, and I have no access to in solving the system. So it's also quite the convergence is also quite difficult, because when you go down with the time increment, there are some numerical problems in some terms of the consistent Jacobian. So it was quite difficult, but anyway, the best convergence was obtained by implicit backward Euler scheme, and we tried also different things, but this was the best one. So some results. This is for just one couple of systems, and so the zero-inclined system, on the zero-inclined system we just identify the self-hardening parameter, okay, of course beside the elastic moduli. These tau naught, tau s, and h0 are the three parameters on the self-hardening equation, and the results are qualitatively not too bad. You got to compare these two blue curve, these two green curve, and these two, I don't know, magenta curve. The brown curve is the one related to no standard crystal plasticity, so no, it's of course independent on the size, and we could obtain this match by setting 0.6 micron for the energetic length scale, which is quite good because the dislocation spacing at the end of the analysis is 0.1, and so we wanted to keep these two parameters, the race sensitivity parameter and the dissipative length scale, as small as possible, but we couldn't do anything less than this. So the worst part of the comparison is just after the yield stress, because in DD many sources of dislocation just activate, so there is this decrease, while the crystal plasticity curve are not as straight as they could be if we could just decrease these two parameters. So, but we cannot, because otherwise we don't converge. If we look at the case with two couples of slip systems, you see the comparison is point-wise worse, of course, but globally it's it's not too bad. The problem just after the yield stress is worse, but at least let me notice that there is a quite nice think that strain gradient crystal plasticity seems to predict, and this is sort of exhaustion of the size effect. You see this 2DD curve for two different sizes, 3 micron and 4.5 micron. There is no size effect, and luckily also the strain gradient model doesn't show any more size effect. And this is not the case if you have just one couple of systems. It just keep going. So it's quite nice. And here the results just for one strip with one couple or two couple. And since I'm running out of time, let me jump to idealize some problem. And first, let me show what we observe for this strip A 1.5 if we don't put our strain gradient extension of the latent hardening. Either no latent hardening or standard latent hardening. These two curves are very close to the case, so you obtain a more compliant answer than the case in which there is just one couple, while our new model is this one. So it's totally far away from the DD response. The other thing I'd like to mention is that we obtain, so gamma 1 is the slip on the less inclined system, gamma 2 is the slip on the more inclined couple of systems, gamma 2 is negative. And this is quite counterintuitive. I don't know whether it is correct or not. Of course, from the thermodynamical viewpoint, it is correct. And let me mention that this more inclined couple of systems is inclined by pi over phi. So the Schmidt factor is still positive, the resolved shear stress is still positive, but this effect is due to the fact is not due to the new latent hardening strain gradient extensions, it's just due to the coupling, due to the use of nice tensor in the defect energy. And in fact, okay, see, this is this plastic slip gamma 2, and this black curve is our new model, and with all the gradients effect, this magenta plot is standard latent hardening, so you see the gamma 2 is even more negative, and the green one is no latent hardening at all, and this effect is just due to the coupling due to nice dislocation density and tensor in the defect energy. So I think I stop here and I jump to the conclusion. Sorry, I was a little bit.
So we have time for questions.
I have a question actually, two questions. The shape of the tau that you wrote with the divergence of C.
The shape of?
Of the tau that you wrote with the divergence of C. If I'm not mistaken, I'm asking, did you model that after Eshelby's theory for the screw dislocation that accounts for image forces?
No. That equation is the. Are you talking about the crystal plasticity model?
Crystal plasticity model, yes.
So I think the first one who obtained this equation was Morton Gerty in 2002, and there is so it's just an extension of the Schmidt law.
No, okay. No, this is something much earlier was done by Eshelby from a material science perspective, but he actually included screw dislocation, so it's fine.
Could be.
Okay. And also, when I had the title of your talk, I thought you would be talking about those nice making a correlation with the experimental results for Pillar's experiment at a small scale, where you actually are observing all these things, both size effects on the first yield event, so the onset of plasticity, and the hardening, which is really hard. And you have an interplay between the microstructural or nanostructural disorder, the dislocation structure, and the small value which confine essentially the size of the dislocation sources. So can you comment on that?
Yes, sure. As I said, implementing strain gradient crystal plasticity code with all these details is quite complicated. So you take this very simple benchmark, which actually has some good feature in it, because this shear mode is one of the most important behavior you observe in this small scale range. So since there are no, as far as I know, useful experiments on this simple shear, we just decided to use discrete dislocation dynamics. Of course, there are many other, for instance, one of the experiments more, in my opinion, more interesting on this aspect is the torsion of thin wires. But then it's a three-dimensional stuff, and if you want to model it with crystal plasticity, you can imagine it's going to be a mess.
You can use that as a benchmark, because now you have tons of experimental data, so this is just a suggestion.
Yes, I appreciate that, but the problem is that we got to implement the code. It's not going to work, at least. I don't know how to do it.
You implemented a boundary condition on the slips, and you fixed the slips at the boundary.
Yeah.
But you only have nice tensor in the defect energy.
No, there is also the dissipative part.
Yeah, it doesn't matter. So for the derivatives which you have, in your case it could be, but in general you can only prescribe the tangential part of the plastic distortion. Of course, you will resolve the plastic distortion in terms of the individual slips, and in your simple case it could be that fixing the tangential part of the plastic distortion is equivalent of fixing the individual slips to zero at the boundary. But this is a check. If you don't do that, you have an inconsistency in the model, because that would partly explain that you have mathematical difficulties.
No, I get your meaning. This is not the case. What you mentioned is absolutely correct if the only higher order variable you use is nice tensor. So you got to account for the number of systems you have on the boundary. But in this case, there is this nice trick, other good feature of allowing for this higher order dissipative term, since you have as independent variables, higher order variable, the gradient of each slip component of each.
Oh, okay.
So
okay.
That's otherwise you got to pay a lot of attention whether the
Got it.
okay.
Great. Thank you.